There's a prison cell around Earth, and most people don't even know they're inside it. The bars aren't made of steel. They're made of distance, time, and the cruel mathematics of physics. You could spend your entire life traveling at impossible speeds and still die without ever leaving our cosmic neighborhood. So here's the question that matters. How far can one human actually travel before their heart stops beating? If you love diving deep into the mysteries of space, please hit that subscribe button. Now let's get started. When we look at the distances between stars, between galaxies, between clusters of galaxies, we're dealing with numbers that our brains weren't designed to comprehend. We evolved on the African savanna, where the farthest thing we needed to see was maybe a predator on the horizon, a few kilometers away. We didn't need to think about distances measured in light years, but here we are, trying to wrap our minds around them anyway. So let's ground ourselves in reality. Let's talk about what we've actually achieved. The fastest humans have ever traveled was during the Apollo 10 mission in 1969. 3 astronauts, Thomas Stafford, John Young, and Eugene Cernan, were returning from a lap around the moon when their capsule hit a peak velocity of 39,897 kilometers per hour. Think about that for a moment. That's almost 40,000 kilometers per hour. That's more than 32 times the speed of sound, and it's still the record for human speed more than 50 years later. But even at that incredible velocity, if you pointed yourself at the nearest star system, Alpha Centauri, which sits 4.37 light-years away, it would take you more than 114,000 years to get there. You'd be dead. Your children would be dead. Your children's children's children, going back thousands of generations, would all be dust by the time that spacecraft arrived. This is the brutal reality of interstellar distances. They're not just far, they're incomprehensibly, devastatingly far. Now you might be thinking, okay, but we've gotten faster since 1969, right? We have. Sort of. Not with humans on board, though. The fastest object we've ever built is the Parker Solar Probe, a spacecraft that's been diving closer and closer to the Sun since its launch in 2018. On December 24, 2024, during its closest approach to our star, the Parker Solar Probe reached a mind-bending 692,000 kilometers per hour. That's 192.22 kilometers per second. That makes it the fastest human-made object in history. Let's put that speed in perspective. At that velocity, you could travel from New York to Tokyo in less than 1 minute. You could circle the entire Earth in about 2 minutes. It's fast, impossibly fast by any standard we're used to. But here's the thing that should humble us all. Even at that record-breaking speed, it would still take more than 6,700 years to reach Alpha Centauri. A human lifespan, even if we're optimistic and say someone lives to be 100 years old, would get you less than 2% of the way there. This is where the conversation gets interesting. Because we're not just talking about distance anymore. We're talking about time. We're talking about human biology. We're talking about the fundamental laws of physics that govern our universe. And we're talking about whether there's any conceivable way around these limitations. So what are our options? If we want to travel farther in one human lifetime, we essentially have 3 paths forward. First, we could try to go faster, much, much faster. Second, we could try to extend human lifespan dramatically, either through biological enhancement, cryogenic freezing, or some other method we haven't invented yet. Third, we could change our definition of what it means to travel, perhaps by sending our consciousness instead of our bodies, or by accepting multi-generational voyages where the people who arrive aren't the people who left. Let's explore the first option, going faster. And this is where physics starts to get really interesting and really limiting. You've probably heard of Einstein's theory of relativity. It tells us that nothing with mass can travel at the speed of light, which is roughly 300,000 kilometers per second, or about 1,079,000,000 kilometers per hour. Light itself travels at this speed because photons have no mass. But anything with mass, including you, me, and any spacecraft we could build, can only approach this speed, never reach it. Why? Because as you accelerate closer and closer to the speed of light, something strange happens. Your mass effectively increases. The faster you go, the more energy you need to accelerate further. As you approach light speed, the energy required approaches infinity. It's like trying to climb a mountain that gets steeper and steeper until the slope becomes vertical. No matter how much energy you pour into it, you can never quite get there. But let's say we could somehow build a spacecraft capable of reaching 99% of light speed. That's still phenomenally fast. At that velocity, you could reach Alpha Centauri in about 4.4 years of Earth time. That's within a human lifetime. Problem solved, right? Not quite. Because there's another aspect of relativity we need to talk about: time dilation. This is one of the most fascinating and counterintuitive predictions of Einstein's theory, and it's been proven correct over and over again through experiments. Time dilation means that time passes differently depending on how fast you're moving. The faster you go, the slower time passes for you, relative to someone who's stationary. If you're interested in understanding why interstellar travel faces such enormous challenges, I've created another video called "The Brutal Truth That Makes Interstellar Travel Impossible" on the card above. I break down the physics and engineering barriers in detail. It's a perfect companion to what we're discussing today. The link is in the description and pinned on the comments. Imagine you're on that spacecraft traveling at 99% of light speed toward Alpha Centauri. From Earth's perspective, your journey takes about 4.4 years, but from your perspective, inside the spacecraft, time is passing much more slowly. At 99% of light speed, time dilation becomes significant. For every year that passes on Earth, only about 63 days pass for you on the spacecraft. So while Earth clocks say your journey took 4.4 years, your clock and your body would experience only about 101 days, just over 3 months. This sounds amazing, right? It means you could theoretically travel much farther than we initially thought, at least from your own perspective. If you could reach 99.9% of light speed, time dilation becomes even more extreme. At that velocity, for every year that passes on Earth, only about 16 days pass for you. You could travel to stars dozens or even hundreds of light years away within your subjective lifetime. But here's where the dream starts to crack. Building a spacecraft that could reach even 10% of light speed is so far beyond our current technology that it might as well be magic. And the faster you want to go, the more impossible it becomes. Not just difficult, impossible. Given what we understand about physics and engineering, let's talk about energy. To accelerate a spacecraft to relativistic speeds, meaning speeds that are a significant fraction of light speed, you need absolutely staggering amounts of energy. A physicist named Gerd Kortemeyer at Michigan State University ran the calculations. He found that accelerating a 10 metric ton spacecraft to 99% of light speed would require more than 200 times the total annual energy consumption of the entire planet Earth. And that's assuming perfect efficiency, which is physically impossible according to the second law of thermodynamics. Where would that energy come from? Our most powerful rockets today use chemical propulsion, burning fuel and expelling it out the back to create thrust. But chemical rockets are pathetically inefficient for interstellar travel. They can only get you to a tiny fraction of light speed before you run out of fuel. Even if you filled your entire spacecraft with fuel, leaving no room for anything else, including you, it still wouldn't be enough. So we'd need something more exotic, nuclear propulsion perhaps. If we could harness nuclear fission or fusion reactions, we'd get much more energy per kilogram of fuel than chemical rockets. Projects like Project Orion, conceived back in the 1950s, proposed using nuclear bombs exploded behind a spacecraft to push it forward. It sounds insane, and it is, but the physics actually works. You could theoretically reach a few % of light speed with that approach, but you'd need thousands of nuclear weapons, a massive spacecraft to absorb the shock, and you'd be spreading radioactive material across space. It's not exactly practical. Then there's antimatter. When matter and antimatter meet, they annihilate each other completely, converting all their mass directly into energy according to Einstein's famous equation, E equals mc squared. This is the most efficient energy conversion possible in the universe. If we could build an antimatter rocket, we could theoretically reach very high speeds, possibly even a significant fraction of light speed. There's just one tiny problem. We can't make antimatter in meaningful quantities. The largest particle accelerators on Earth can produce only minuscule amounts, and it takes vastly more energy to create it than you get back. Plus, storing antimatter is nearly impossible because it explodes the instant it touches regular matter. Some scientists have proposed using light itself as propulsion. Projects like Breakthrough Starshot imagine using ground-based lasers to push tiny spacecraft equipped with light sails. Light carries momentum, and when photons bounce off a reflective sail, they transfer that momentum to the spacecraft. If you had powerful enough lasers, you could accelerate a small probe to 20% of light speed. The catch? The probe would need to be incredibly small, maybe just a few grams, about the weight of a paperclip. There's no way to scale this up to carry humans. You'd be vaporized by the laser before you got anywhere. What about something even more speculative? Warp drives, like in science fiction, where you bend space itself around your spacecraft. You wouldn't be moving through space. Space would be moving around you. This idea actually has some basis in real physics. In 1994, a physicist named Miguel Alcubierre published a paper showing that Einstein's equations theoretically allow for a warp drive. You'd compress space in front of you and expand it behind you, creating a bubble that carries you along faster than light, at least relative to the space outside the bubble. Sounds perfect, right? Unfortunately, there are some rather severe problems. First, the Alcubierre drive would require something called exotic matter with negative mass or negative energy density. We've never observed anything like this in nature, and we have no idea if it even exists or how to create it. Second, the energy requirements are astronomical. Early calculations suggested you'd need more energy than exists in the entire observable universe just to move a small spacecraft. More recent refinements have brought that number down, but it's still far beyond anything we could generate. Third, there's the causality problem. If you can travel faster than light, you might be able to travel backward in time, which creates all sorts of paradoxes that physics doesn't know how to handle. So faster than light travel, as far as we know, is off the table. At best, we might someday reach a few % of light speed using nuclear or fusion propulsion. Let's be optimistic and say we could hit 10% of light speed. That's still 30,000 kilometers per second, which would be an incredible achievement. At that velocity, you could reach Alpha Centauri in about 43 years. That's a human lifetime, barely. If you left Earth at age 25, you'd arrive at age 68, assuming you survived the journey. But would you survive? Because speed isn't the only problem. There's the small matter of staying alive for 4 decades in the hostile environment of space. And this brings us to the second option for traveling farther, extending human lifespan or preserving the body somehow. Space is not friendly to human bodies. It's not just empty, it's actively hostile. First, there's radiation. Here on Earth, we're protected by our planet's magnetic field and atmosphere, which block most of the harmful radiation from the sun and from deep space. But once you leave Earth's protective bubble, you're exposed to constant bombardment from cosmic rays, high-energy particles traveling at nearly the speed of light. These particles can tear through spacecraft hulls, through your body, damaging DNA and increasing your risk of cancer dramatically. The astronauts who went to the moon were only exposed to this radiation for a week or so. They got lucky. No major solar storms occurred during their missions. But a multi-decade journey to another star, you'd be absorbing radiation the entire time, even with shielding, which adds weight and makes your spacecraft harder to accelerate. You'd likely develop cancer long before you reached your destination. We'd need to develop much better radiation shielding, perhaps using magnetic fields similar to Earth's, or we'd need to find a way to repair DNA damage faster than it accumulates. Then there's the issue of bone density and muscle mass. In microgravity, your bones and muscles don't have to work as hard as they do on Earth. Your body, being efficient, starts to break them down. Astronauts on the International Space Station, which orbits just a few hundred kilometers above Earth, lose about 1 to 2% of their bone density per month. Even with rigorous exercise programs, they're still losing mass. On a decades-long voyage, without some form of artificial gravity, you'd arrive at your destination with bones so fragile they might snap under the slightest stress. We could potentially solve this with rotating spacecraft that create artificial gravity through centrifugal force. You've probably seen this in science fiction, a big wheel or cylinder spinning in space, pushing you against the outer wall. The physics works. It's just incredibly difficult to build a structure that's large and strong and then accelerate it to relativistic speeds. The engineering challenges multiply with every requirement we add. There's also the psychological challenge. Imagine spending 40 years in a metal can with the same handful of people, with no possibility of escape, no fresh air, no new faces, no horizon to look at. Studies of isolated environments like Antarctic research stations and nuclear submarines show that humans struggle with prolonged isolation. Depression, anxiety, interpersonal conflicts, these all become serious issues. We're social creatures who evolved in dynamic environments with changing scenery and new stimuli. A decades-long spaceflight would test the limits of human psychology. So what if we just skip the whole being conscious part of the journey? This brings us to cryogenic freezing or suspended animation. The idea is simple. Cool the body down to a temperature where all biological processes essentially stop, preserve it for decades, then warm it back up when you arrive. No need for food, water, or entertainment during the journey. You'd just go to sleep on Earth and wake up at Alpha Centauri. We can already do something like this, sort of. Hospitals use therapeutic hypothermia to cool patients down to around 33 degrees Celsius for a few hours during certain medical procedures. This slows metabolism and protects the brain from injury. But we're talking about cooling someone down much further, close to freezing, and keeping them that way for decades. That's a completely different challenge. The problem is ice crystals. When you freeze biological tissue, water inside the cells expands and forms sharp ice crystals that tear through cell membranes and structures. When you thaw the tissue, it's mush. This is why frozen strawberries are soggy when you defrost them. Your brain wouldn't fare any better. Some scientists are exploring vitrification, a process where you replace the water in cells with special chemicals called cryoprotectants, then cool the tissue so quickly that it solidifies into a glass-like state without forming ice crystals. This has worked with tiny organisms like nematode worms and with small tissue samples, but scaling it up to an entire human body, then keeping that body stable for decades, then reversing the process without causing damage, We're nowhere close to making that work. There's also the question of the brain. Your memories, your personality, everything that makes you you, is encoded in the precise connections between billions of neurons. Would those connections survive freezing and thawing? Even if your body survived, would you still be you when you woke up? We don't know, and we won't know until we try it, which raises some serious ethical questions. Another option is hibernation, similar to what bears do in winter. Their metabolism slows down, their body temperature drops, but they don't freeze solid. They're in a state of reduced biological activity that conserves energy. If we could induce something similar in humans, we might be able to slow aging and reduce the need for resources during a long journey. Some research suggests this might be possible using specific drugs or by manipulating certain metabolic pathways. But even bears don't hibernate for 40 years straight. They wake up periodically, and their hibernation only lasts a few months. Extending that to decades is purely speculative at this point. So let's say we can't go faster than about 10% of light speed, and we can't reliably freeze or hibernate humans for decades. What's left? This brings us to the third option, changing what we mean by travel. Maybe the people who leave Earth aren't the people who arrive at the destination. Maybe we embrace multi-generational starships. A generation ship is exactly what it sounds like. A massive spacecraft designed to support a complete human society for hundreds or thousands of years. You'd launch with a founding population of maybe a few hundred or a few thousand people. They'd live their entire lives on the ship, have children, and those children would have children, and so on, until eventually, many generations later, their descendants would arrive at the destination star system. The people who arrive would have never known Earth except through stories and records. This concept has a certain poetry to it. It's a commitment not just by individuals, but by an entire lineage. It's humanity saying, we're willing to sacrifice our chance to see the stars so that our great-great-great-grandchildren might walk on alien worlds. But it comes with profound challenges. First, you'd need a truly enormous spacecraft. It would have to be a self-contained ecosystem capable of producing food, recycling air and water, and providing living space for thousands of people. You'd need farms, factories, hospitals, schools, and entertainment. You'd need to bring enough genetic diversity to avoid inbreeding over many generations. You'd need redundancy in every system because there's no calling for help if something breaks. The International Space Station, which supports just 6 to 7 people and relies on regular resupply missions from Earth, costs billions of dollars to maintain. Scaling that up to a self-sufficient city-sized vessel is almost unimaginable with current technology. Then there's the social challenge. How do you maintain a stable society for hundreds of years in such a confined space? What happens when conflicts arise? What if future generations decide they don't want to continue the mission? What if they want to turn the ship around or mutiny against the mission planner's original vision? You can't exactly have elections where the outcome is let's go home, when home is dozens of light years behind you, and you've already spent lifetimes getting where you are. Some researchers have studied isolated communities on Earth, places like islands or space stations, to understand how social structures might hold up during a generation ship voyage. The findings aren't always encouraging. Small populations can develop rigid social hierarchies, groupthink, and insularity. Innovation can stagnate. Conflicts can escalate with nowhere to escape. You'd need incredibly careful social engineering, cultural practices, and governance structures to keep a generation ship functioning for centuries. It's as much a social experiment as a technical one. There's also the question of purpose. The founding generation might be motivated by the dream of reaching a new world. But what about their children, who had no choice in the matter? What about their grandchildren who might resent being born into a mission they never agreed to? Maintaining morale and a sense of purpose across generations would be one of the hardest challenges of all. But let's imagine we solve all those problems. We build the ship, we launch it, and somehow the society on board remains stable and functional for the duration of the journey. At 10% of light speed, reaching Alpha Centauri would take about 43 years. That's just 1 or 2 generations, barely enough to call it a generation ship. But Alpha Centauri might not have habitable planets. If we wanted to reach a star system we know has potentially habitable worlds, like TRAPPIST-1, which is about 39 light-years away, the journey would take 390 years. That's roughly 15 to 20 generations. Your great-great-great-great-great-great-great-great-great-great-great-grandchildren would be the ones to arrive. Or we could aim for something closer and more certain. Proxima Centauri b, an exoplanet orbiting the closest star to us, Proxima Centauri, is about 4.24 light-years away. It orbits within its star's habitable zone, meaning liquid water could theoretically exist on its surface. At 10% of light speed, you'd get there in about 42 years. That's achievable within a long human lifetime or across 2 generations. But we don't know much about Proxima Centauri b yet. It might be tidally locked, with one side always facing the star and the other in permanent darkness. It might be bombarded by radiation from stellar flares. It might not have an atmosphere. We're sending our descendants on a journey of decades based on what might turn out to be false hope. This is the cruel irony of interstellar travel. The places close enough to reach in a reasonable time might not be worth reaching. The places we know are worth reaching are too far away, and we can't know for sure until we get there, which requires committing enormous resources and human lives to what might be a dead end. Now, let's talk about another approach that sidesteps the need for physical bodies altogether: uploading consciousness. What if, instead of sending your body across the stars, you could send your mind? Your memories, personality, and consciousness could be digitized and transmitted as information, traveling at the speed of light, and then reconstructed at the destination in a new body, whether biological, robotic, or virtual. This idea appears regularly in science fiction, and some scientists and futurists take it seriously. The Human Connectome Project and similar research initiatives are working to map the brain's neural connections in incredible detail. The idea is that if we understand the brain well enough, we might be able to simulate it in a computer, creating a digital copy of a person's mind. That digital mind could then be transmitted across space as a radio signal, taking only 4.24 years to reach Proxima Centauri, the same time it takes light to get there. But this raises some profound questions. First, would a digital copy of your mind actually be you? Or would it be a separate entity that just thinks it's you? If we scan your brain and create a simulation, the original you is still here on Earth. The copy at Proxima Centauri might have all your memories and think it's continuous with your identity, but from your perspective on Earth, you're still here. You didn't travel anywhere. Your copy did. This is the philosophical problem of personal identity, and we don't have a clear answer. Some philosophers argue that identity is tied to physical continuity. You are your body, and a copy is not you no matter how perfect it is. Others argue that identity is informational. If a system contains the same information and functions the same way, it is you, regardless of the substrate. Still others argue that what matters is psychological continuity. As long as the being at the destination has your memories and feels like a continuous extension of your past self, that's enough to call it you. There's no consensus, and depending on which view you take, mind uploading is either the ultimate form of immortality and space travel, or it's a philosophical trap that creates copies while the original you stays behind or dies. There's also the technical challenge. We're nowhere near being able to scan a human brain at the resolution needed to capture every neuron and synapse, let alone the molecular and possibly quantum processes that might be essential to consciousness. The human brain contains roughly 86 billion neurons, each connected to thousands of others, forming trillions of synapses. The data storage required to represent all that information would be measured in petabytes or exabytes, and that's just storage. Actually simulating a brain in real time, processing all those connections and interactions would require computational power far beyond anything we have today. Even if we could scan and simulate a brain, we'd need to transmit that information across interstellar distances. A radio signal traveling at light speed would take years to reach even the nearest stars. And space isn't empty. There's dust, gas, and radiation that could corrupt the signal. You'd need error correction, redundancy, and incredibly powerful transmitters and receivers. The Voyager 1 spacecraft, launched in 1977 and now over 23 billion kilometers from Earth, transmits data at a measly 160 bits per second, and we can barely hear it. Sending the petabytes of data needed to encode a human mind across light years would be an engineering feat of staggering proportions. And let's say we solve all that. Let's say we can scan, simulate, and transmit a human mind. What waits at the destination? If you're going to reconstruct the mind, you need infrastructure there. Computers, power sources, maybe robots or biological bodies to house the consciousness. But who's going to build that infrastructure? You'd need to send a robotic mission first, decades or centuries ahead, to set up the necessary equipment. That mission would need to be fully autonomous, capable of mining resources, manufacturing components, and assembling complex systems without any human guidance. We're talking about self-replicating machines, which introduces a whole other set of risks and ethical concerns. So mind uploading, while fascinating, is also deeply speculative, both technologically and philosophically. It might become possible someday, but it's not a solution we can count on in the near term, and it fundamentally changes what we mean by travel. If you're not taking your body, if you're not experiencing the journey, are you really going anywhere? Or are you just creating a distant copy of yourself while you stay home and live out your life on Earth? Let's step back and look at this from another angle. Maybe the question isn't how far humans can travel in one lifetime. Maybe the question is, what does one lifetime even mean in the context of space exploration? Our lifespans are defined by biology, by the ticking clock of cellular aging, DNA damage, and accumulated wear and tear. But those limitations aren't set in stone. They're the result of evolution, which optimized us for survival and reproduction on Earth, not for interstellar voyages. There's growing research in the field of longevity science aimed at extending healthy human lifespan. Scientists are studying organisms that live far longer than we do. There are species of jellyfish that can theoretically live forever by reverting to earlier life stages. Certain whales live over 200 years. Naked mole rats seem almost immune to cancer. If we could understand the mechanisms behind these extended lifespans and apply them to humans, we might be able to extend our time dramatically. Some researchers are focusing on senescence, the process by which cells stop dividing and start secreting harmful substances that contribute to aging. If we could clear out senescent cells or prevent them from forming, we might slow aging. Others are looking at telomeres, the protective caps on the ends of chromosomes that shorten each time a cell divides. When telomeres get too short, cells die. If we could maintain telomere length, we might extend cell lifespan, and by extension human lifespan. There are also more radical proposals. What if we replace aging organs with lab-grown ones? What if we use nanotechnology to repair cellular damage as it occurs? What if we genetically engineer humans to be more resistant to radiation, to require less food and water, to hibernate like bears, or to tolerate microgravity better. These aren't fantasy ideas. They're serious areas of research, though we're still in the very early stages. If we could extend human lifespan to 200, 300, or even 500 years, suddenly those multi-decade journeys become much more feasible. A 40-year trip to Alpha Centauri would be just a fraction of your life, like a long career or a phase of your existence, rather than the defining journey of your entire lifespan. You could leave Earth at 50, arrive at 90, and still have centuries of life ahead of you to explore your new home. But extending lifespan comes with its own set of challenges. Would your mind be able to handle centuries of experience? Would you run out of storage capacity for memories? Would psychological problems compound over time? And there are societal questions too. If only a wealthy elite can afford life extension treatments, does that create a permanent underclass of short-lived people? Who gets to go on the interstellar missions? These are questions we'd need to grapple with long before we launch anyone into deep space. Here's another reality check. Even if we solve the technical challenges, even if we build the ships and extend human lifespans and figure out cryogenics or mind uploading, there's still a more fundamental question. Should we even try? Interstellar travel would require an enormous investment of resources, energy, and human effort. Some argue that those resources would be better spent solving problems here on Earth. Climate change, poverty, disease, inequality. Why spend trillions of dollars sending a handful of people to another star when billions of people on our own planet lack basic necessities? There's a counter-argument, though. Humanity has always been a species of explorers. We left Africa tens of thousands of years ago and spread across the entire planet, crossing oceans, mountains, and deserts. Exploration is part of who we are. It's driven scientific discovery, technological innovation, and cultural exchange. And there's a practical reason too. Putting all our eggs in one basket, one planet, is risky. A single catastrophic event, whether an asteroid impact, a supervolcanic eruption, nuclear war, or runaway climate change, could potentially wipe out our species. Becoming a multi-planetary or even multi-stellar species would be an insurance policy for humanity's long-term survival. Plus, the technologies we'd develop for interstellar travel could have applications here on Earth. Advanced propulsion systems, closed-loop life support, radiation shielding, these could help us live more sustainably and protect ourselves from various threats. The Apollo program, which put humans on the moon, gave us innovations in computing, materials science, and telecommunications that we still benefit from today. An interstellar program could have similar spin-off benefits, but let's be honest, we're not launching an interstellar mission anytime soon. The technical, financial, and social challenges are simply too great with our current level of development. What we can do, and what we are doing, is laying the groundwork. We're sending robotic probes to explore our solar system. We're building better telescopes to study exoplanets and identify potentially habitable worlds. We're researching advanced propulsion concepts. We're studying the effects of long-duration spaceflight on the human body through missions on the International Space Station and planning longer missions to the Moon and Mars. Mars, in particular, is often seen as the proving ground for interstellar travel. It's relatively close, just a few months away with current technology, and while it's harsh, it's far more accessible than any exoplanet. If we can establish a self-sustaining colony on Mars, we'll learn invaluable lessons about living off Earth, about closed-loop ecosystems, about governing isolated communities, about all the things we'd need to know for a generation ship or an interstellar colony. Mars is our practice run. NASA's Artemis program aims to return humans to the Moon this decade, with the goal of establishing a permanent presence there. The European Space Agency, China's space program, and private companies like SpaceX are all developing capabilities for lunar and Martian exploration. SpaceX's Starship, currently in development, is designed to carry up to 100 people and could theoretically be used for interplanetary travel within our solar system. Elon Musk has stated his goal of making humanity a multi-planetary species, with Mars as the first step. These aren't just dreams anymore. They're active projects with timelines, budgets, and hardware being built and tested right now. And while Mars is still within our solar system, the skills and technologies we develop there will be essential if we ever want to go beyond. There's also the question of what we do when we got to another star system. Let's say we somehow make it to Proxima Centauri b after 40-something years of travel. We arrive in orbit around an alien world. Now what? We can't just land and set up camp. We don't know what the atmosphere is like, if there even is one. We don't know what the surface temperature is, what the gravity is like, whether there's water, whether there's life. And if there is life, we have to be incredibly careful not to contaminate it with Earth organisms or to expose ourselves to alien microbes that could be harmful. We'd need to conduct extensive surveys first, probably with robotic landers and rovers, similar to what we've done on Mars. We'd need to test the soil, the air, the water if there is any. We'd need to identify resources we could use: water ice for drinking and making fuel, minerals for construction, perhaps organic compounds for growing food. Only after we're confident it's safe would we consider sending humans down to the surface, and even then, we might need habitats, enclosed environments with controlled atmospheres, at least at first. We might need to terraform, gradually altering the planet's environment to make it more Earth-like. That could take centuries or millennia, depending on the planet's starting conditions. So the timeline for actually living on an exoplanet, walking around on the surface breathing the air, could be far longer than the travel time to get there. This brings up an interesting thought experiment. If the journey takes 40 years and establishing a livable environment takes another 100 years, you're looking at 140 years minimum from launch to the first child born on that world who can step outside without a spacesuit. That's multiple generations. The people who make the decision to go will never see the fruits of their labor. Their great-grandchildren might. Is that worth it? That's a question each generation has to answer for itself. But consider this. The people who built the great cathedrals of medieval Europe knew they'd never see them completed. Construction often took over a century, yet they built them anyway because they believed in something larger than themselves, a legacy that would outlast their individual lives. Interstellar colonization would be similar. It's a cathedral built across the stars, a project that spans generations, driven not by personal gain, but by a vision of humanity's future. Now let's get really speculative, because why not? We've covered the plausible, the difficult, and the barely possible. Let's venture into the realm of far future possibilities that are theoretically allowed by physics, but so far beyond our current capabilities that they might as well be magic. Because if we're asking how far humans could really travel in one lifetime, we should at least look at the absolute theoretical limits. One concept that comes up is the use of wormholes, theoretical shortcuts through space-time. Einstein's general relativity allows for solutions where space-time is bent so severely that two distant points in the universe are connected by a tunnel, a wormhole. If you could enter one end, you'd instantly emerge at the other, potentially light years away, without having traveled the space in between. Wormholes are mathematically consistent with our understanding of physics, but there are massive caveats. First, we've never observed a wormhole. We don't know if they exist naturally, and if they do, they might be microscopic, lasting only fractions of a second. Second, even if a wormhole existed, It would likely collapse immediately unless it was held open by exotic matter with negative energy density, the same stuff we'd need for a warp drive, which we've never seen and don't know how to create. Third, even if you could stabilize a wormhole, you can't create a shortcut to somewhere you've never been. The wormhole has to connect 2 points, which means you'd have to physically travel to the destination, first by conventional means, drag one end of the wormhole with you, and only then could you use it as a shortcut. So it doesn't help with the initial journey. It could, however, allow for rapid travel between established colonies, turning a multi-decade journey into an instantaneous hop. But that's assuming we ever figure out how to create and stabilize wormholes in the first place, which is a very big if. Another wild idea is the concept of black hole time dilation. Near a black hole, gravity is so strong that it warps time itself. The closer you get to the event horizon, the slower time passes for you relative to the rest of the universe. In the movie Interstellar, the characters visit a planet near a supermassive black hole where 1 hour on the surface equals 7 years back on Earth. That's an exaggeration for dramatic effect, but the principle is real. If you could safely orbit close to a black hole, time would pass more slowly for you than for the universe outside. You could experience, say, 10 years while hundreds or thousands of years pass in the wider universe. When you leave the black hole's influence and travel to your destination, you'd arrive in the distant future. In a sense, you'd be traveling forward in time without aging much yourself. But this doesn't help you cover more distance in your subjective lifetime. It just means you arrive in a future era. And finding a black hole to use, getting close enough without being torn apart by tidal forces, and then escaping its gravity well would require absurd amounts of energy and technology. There's also the Tipler cylinder, another exotic theoretical concept. If you could create an infinitely long, incredibly dense rotating cylinder, the rotation would drag space-time around it in such a way that you could theoretically travel in a closed time-like curve, essentially traveling backward or forward in time. But building an infinitely long cylinder of ultra-dense matter is, to put it mildly, not practical. It's more of a mathematical curiosity than a real engineering proposal. The point of mentioning these ideas isn't to suggest they're plausible in any near-term or even far-term sense. It's to show that physics, as we currently understand it, allows for some truly bizarre possibilities. The universe is stranger than we often give it credit for, but it's also governed by laws that seem designed to keep certain things, like faster-than-light travel or time travel, just out of reach. Every loophole comes with impossible requirements or devastating consequences. So where does that leave us? If we're being realistic, based on our current understanding of physics and our current level of technology, here's what seems achievable within a human lifetime. Within our solar system, we can go pretty much anywhere, given enough time and resources. Mars is a few months away. The outer planets take years, but they're doable. We've already sent probes to every planet, and we've sent spacecraft beyond the solar system entirely. Voyager 1 is now in interstellar space, over 23 billion kilometers from Earth, and it's been traveling for nearly 50 years. If a human could survive that long in space, they could make it that far too, though they'd still be nowhere near another star. For actual interstellar travel, to reach another star system within a human lifetime, we'd need speeds of at least 10 to 20% of light speed. That would get us to the nearest stars, like Proxima Centauri, in 20 to 40 years. But achieving those speeds requires propulsion systems we don't have yet. Nuclear pulse propulsion, fusion rockets, antimatter drives, or laser light sails. These are theoretically possible, but would require massive technological advances and resources. If we're willing to bend the definition of one lifetime, we have more options. We could extend human lifespan through medical advances, making a 100-year journey more palatable. We could use generation ships where the traveler's descendants complete the journey. We could develop reliable cryogenic freezing or induced hibernation. We could explore mind uploading if we can solve the technical and philosophical challenges. Each of these approaches has profound implications, not just technologically, but socially, ethically, and existentially. And if we're willing to be really optimistic, to bet on breakthrough discoveries in physics, then maybe, just maybe, we could find a way to manipulate space-time itself, to warp space or create wormholes or exploit some other loophole in the fabric of reality. But those are bets on unknowns. They're dreams, not plans. The honest answer to your question is this: with current technology, a human being could travel maybe to Mars and back in one lifetime, covering at most a few 100 million kilometers. With near-future technology, the kind we're actively developing, we could probably reach the outer solar system billions of kilometers within a long lifetime. With far-future but still plausible technology, we could potentially reach the nearest stars, covering tens of trillions of kilometers within an extended or modified human lifetime. And with truly speculative technology, based on physics we don't fully understand yet, the limits might be much, much higher, potentially allowing us to cross the galaxy or beyond. But there's something else worth considering. When we talk about how far humans can travel, we're often thinking about distance as the primary measure, but maybe that's the wrong metric. Maybe what matters isn't how far you go, but what you discover, what you experience, what you learn. The astronauts who went to the moon only traveled about 384,000 kilometers from Earth. That's nothing compared to the scale of the solar system, let alone the galaxy. But they saw something no human had ever seen before. They stood on another world, looked back at Earth hanging in the void, and gained a perspective that changed them and, through their accounts, changed all of us. In that sense, even a journey to Mars, just a few 100 million kilometers, would be profound. The first humans to set foot on Mars will be farther from Earth than anyone in history. They'll see 2 sunsets, watch Earth rise and set in the Martian sky as a bright blue star, experience a gravity 1/3 of what they're used to, and live in a place where the sky is butterscotch-colored and the landscape is rust-red as far as the eye can see. They'll be pioneers in the truest sense, venturing into territory where humans have never been, where every step is a first. And if we do eventually make it to another star, even if it takes generations or requires us to transform what it means to be human, even if the people who arrive are radically different from the ones who left, that will be one of the greatest achievements in the history of life on Earth. Because for billions of years, life has been confined to one small planet circling one ordinary star. Making the jump to another star system would be life and humanity transcending its birthplace and taking its first real steps into the galaxy. If you are enjoying it, please subscribe to the channel. I am just starting, and your help makes all the difference. There's a thought that keeps coming up in discussions about interstellar travel, one that's both humbling and inspiring. Carl Sagan, the astronomer and science communicator, put it beautifully. He called us star stuff contemplating the stars. The atoms in our bodies were forged in the cores of dying stars billions of years ago. We are, quite literally, made of the same material as the stars we look up at. In a very real sense, interstellar travel would be the universe becoming conscious of itself, matter that was scattered across the cosmos reuniting, star stuff returning to the stars. That's poetic, but it's also true. And it points to why we're drawn to space exploration despite the enormous challenges. It's not just about survival or resources or curiosity, though those are all part of it. It's about the fundamental human drive to explore, to push boundaries, to see what's over the next hill, across the next ocean, or around the next star. It's the same drive that led our ancestors out of Africa. across the Bering Strait to the islands of the Pacific. We're a species of wanderers, and space is the ultimate frontier. But we also have to be realistic. Space is hard, it's unforgiving, it doesn't care about our dreams or our ambitions. Every meter we travel beyond Earth is earned through ingenuity, sacrifice, and an enormous expenditure of energy and resources. And the distances involved in interstellar travel are so vast that they challenge not just our technology but our very sense of what's possible. Consider this. If you could shrink the solar system down so that the Sun was the size of a basketball, Earth would be about 22 meters away, roughly the length of a tennis court. Neptune, the outermost planet, would be about 680 meters away, more than half a kilometer. That's our solar system. Now, where would the nearest star be on this scale? Not in the next town over, not in the next country. It would be about 6,000 kilometers away. If the Sun were a basketball in New York City, the nearest star would be a basketball in Rome, Italy. That's the scale we're dealing with. The distances between stars are incomprehensibly vast, and crossing them will require either incredible patience, spanning generations, or incredible breakthroughs in technology, or both. It's easy to get discouraged by those numbers, to think it's hopeless, that we're forever trapped in our solar system. But remember, a little over a century ago, the idea of flying across the Atlantic Ocean seemed absurd. 68 years passed between the Wright brothers' first flight and Neil Armstrong stepping onto the moon. Technology advances, sometimes slowly, sometimes in leaps. We don't know what discoveries await us in the coming decades or centuries. We don't know what new physics might be uncovered, what new technologies might be invented, what new materials or energy sources we might harness. 50 years ago, the idea of having a supercomputer in your pocket that could access the sum of human knowledge instantly would have seemed like science fiction. Today we call it a smartphone. Who knows what will seem commonplace 50 or 100 years from now? There's also the possibility that we're not alone. If intelligent life exists elsewhere in the galaxy, and if any of those civilizations are significantly more advanced than us, they might have already solved the problems we're struggling with. They might have faster than light travel, or they might have found ways to manipulate space-time, or they might exist as post-biological entities who don't need planets at all. If we ever make contact with such a civilization, they could share knowledge that would leapfrog our development by centuries or millennia. Of course, that's a big if. We haven't detected any signs of alien intelligence despite decades of searching with projects like SETI, the search for extraterrestrial intelligence. The Fermi paradox asks, if the universe is so vast and old, and if life and intelligence can arise, where is everybody? Why haven't we seen evidence of alien civilizations? There are many possible answers, ranging from the optimistic, that they're out there, but we haven't looked hard enough or in the right ways, to the pessimistic, that intelligent civilizations inevitably destroy themselves before they can spread to the stars, to the unsettling, that there's some unknown barrier, some great filter that prevents life from advancing beyond a certain point. We don't know which answer is correct, or if any of them are. But the possibility that we might be alone, or nearly alone, in the galaxy makes our survival and expansion even more important. If we're the only ones who can ask these questions, the only ones who can appreciate the beauty and complexity of the universe, then we have a responsibility not just to ourselves but to the cosmos itself, to survive, to explore, to understand. Let's talk numbers one more time, but in a different way. Let's talk about what it would actually take to mount an interstellar mission with something like current or near-future technology. Let's say we want to send a small crew, maybe 10 people, to Proxima Centauri using a nuclear pulse propulsion system, one of the more realistic near-term propulsion concepts. We want to get them there in 40 years. which means we need to accelerate to about 10% of light speed and then decelerate when we get there. The math is brutal. To accelerate even a small spacecraft to 10% of light speed using nuclear bombs would require thousands of detonations, each perfectly timed and positioned. You'd need to carry all those bombs with you, which means an enormous amount of mass, and every bit of mass you add means you need more energy to accelerate it, which means more bombs, which means more mass in a vicious cycle. Let's say, conservatively, that the total mass of the spacecraft, including fuel, life support, crew, supplies, and the lander for the destination, is around 50,000 tons. That's about the mass of a large naval destroyer. To accelerate that to 10% of light speed would require energy on the order of 10 to the 18 joules, or about 1 exajoule. For comparison, total global energy consumption per year is around 600 exajoules. So you'd need roughly 1/600th of humanity's total annual energy output just to accelerate one ship. And you'd need that much again to decelerate at the other end. Where would that energy come from? Nuclear bombs, in theory, but you'd need thousands of them, each weighing several hundred kilograms. The bombs themselves would add to the mass of the ship, making the problem worse. Some designs, like Project Daedalus from the 1970s, proposed using fusion reactions in pellets rather than fission bombs, which would be more efficient and could theoretically get you to higher speeds. But we still haven't achieved sustained fusion power on Earth, let alone in a spacecraft. Then there's the cost. Estimates for a realistic interstellar probe mission, not even a crude one, just a small probe using laser light sail technology, run into the billions or tens of billions of dollars. A crude mission would be orders of magnitude more expensive. You're looking at hundreds of billions, possibly trillions of dollars. For comparison, the International Space Station, the most expensive single object ever built, cost about $150 billion over several decades. An interstellar mission would dwarf that. Could humanity afford it? In absolute terms, yes. The global economy produces roughly $100 trillion per year in GDP. If every nation on Earth agreed to dedicate, say, 1% of global GDP to an interstellar mission, that would be $1 trillion per year. Spread over a few decades, you could probably build the ship, but getting that level of international cooperation and sustained funding would be the real challenge. Space programs are always vulnerable to budget cuts and shifting political priorities. An interstellar mission would need support that spans multiple generations of politicians and citizens who would never live to see the results. That's why some people argue that the first interstellar missions might be funded not by governments, but by billionaires or private consortia. Someone like Elon Musk or Jeff Bezos or their future equivalents could potentially dedicate their vast fortunes to an interstellar project. It would be the ultimate legacy, funding a mission that could outlive them by centuries. But even billionaire funding has limits, and the costs would still be staggering. There's another option that's often overlooked. We could send the data, not the people. Instead of trying to transport biological humans across light years, we could send information, detailed genetic sequences, medical knowledge, cultural archives, art, music, literature, everything that defines humanity could be encoded into data and transmitted via radio or laser to a destination where robotic systems would receive it and use it to recreate human civilization. You could even include the instructions to build humans from scratch. If the destination has the right equipment, autonomous robots could synthesize DNA based on the transmitted sequences, grow embryos in artificial wombs, and raise the resulting children using AI programmed with human knowledge and values. It sounds like science fiction, but every piece of it is based on technologies that are either already emerging or theoretically possible. Gene synthesis, artificial wombs, advanced AI. This approach would solve several problems. Data can be transmitted at the speed of light, so the travel time is just the light travel time, 4.2 years to Proxima Centauri, instead of 40 or more. You don't need life support or massive amounts of fuel. You don't need to keep humans alive for decades. The data package could even be sent to multiple destinations simultaneously, seeding humanity across many star systems. But it raises profound questions. Are those reconstructed humans really us? They'd have our genes, our knowledge, our culture, but they'd grow up on an alien world, raised by machines, with no direct connection to Earth or to biological parents. Would they consider themselves human? Would they identify with the civilization that sent them? And is this really space travel? Or is it just spreading our blueprint like dandelion seeds carried on the wind, hoping something takes root? These are philosophical questions as much as technical ones, and they get at the heart of what we mean when we talk about humans traveling through space. Are we talking about moving our biological bodies, or are we talking about preserving and spreading human consciousness, human knowledge, human culture? Depending on how you answer that question, the limits change dramatically. If consciousness can be digitized, if a human mind can be uploaded to a computer substrate, and that substrate can be transmitted as data, then the speed limit becomes the speed of light for information, not for matter. You could travel to another star system in years rather than decades or centuries. Your body would stay behind or perhaps wouldn't matter at all anymore. You'd exist as information, as patterns of data, experiencing reality through whatever sensors and interfaces were available at your destination. This veers into transhumanism, the idea that humans can and should use technology to transcend our biological limitations. It's controversial. Some people see it as the logical next step in human evolution, a way to overcome disease, aging, and the constraints of flesh. Others see it as a loss of what makes us human, a surrender of our biological heritage, and the embodied experience that defines human life. There's no easy answer. But it's worth noting that humans have always used technology to transcend our limitations. We can't fly, so we built airplanes. We can't survive underwater, so we built submarines. We can't remember everything, so we invented writing and computers. In a sense, we've always been cyborgs, organisms that rely on tools and technology to extend our capabilities. The question is just how far that process can and should go. Let's pull back from the philosophical deep end for a moment and talk about something more concrete. The actual experience of long-duration space travel. What would it be like to spend years or decades on a spacecraft, knowing you might never see Earth again, that everyone you knew before you left will be older or dead by the time you arrive, if you arrive at all? Astronauts on the International Space Station spend about 6 months in space, and even that takes a toll. Microgravity causes muscle atrophy and bone loss despite rigorous exercise regimens. Cosmic radiation increases cancer risk. The isolation and confinement can lead to psychological stress, even with regular communication with Earth and the knowledge that you'll be home in a few months. Now multiply that by 10 or 20 or 50. How do you maintain physical and mental health over decades in a confined artificial environment? You'd need artificial gravity, probably generated by rotating the spacecraft. You'd need robust shielding against radiation. You'd need a complete life support system that can recycle air, water, and waste indefinitely with minimal outside input. You'd need food production, either by carrying enough supplies for the entire journey, which adds enormous mass, or by growing food on board, which requires space, light, water, and nutrients. You'd need a social structure that can handle conflicts and maintain morale over the long term. You'd need meaningful work and recreation to prevent boredom and depression. Some of these challenges have been studied in analog environments on Earth. Projects like Mars 500 simulated a 520-day mission to Mars by sealing volunteers in a mock spacecraft in Moscow. The crew dealt with isolation, confinement, communication delays, and monotony. They came through it successfully, proving it's possible, but they also knew they were on Earth, that they could leave in an emergency, that it was temporary. A real interstellar voyage would have none of those psychological safety nets. There's also the question of governance. Who's in charge on a generation ship or a decades-long mission? The crew who left Earth will age and eventually die, replaced by those born on the ship. What legal and social structures apply? Are they bound by the laws of their nation of origin? Even though they're light years away, do they form their own government? What if different factions emerge with different goals, some wanting to continue to the destination, others wanting to turn back or settle somewhere else? These aren't idle questions. History is full of exploratory expeditions that ended in mutiny or internal conflict. And what about reproduction? On a generation ship, children would be born and raised in space, never setting foot on a planet until they reach the destination, if they do. What kind of childhood is that? What kind of education do they receive? Do they resent their parents and grandparents for making a decision that condemned them to life on a spacecraft? Or do they embrace the mission, seeing themselves as pioneers in a grand endeavor? Science fiction has explored these ideas extensively. Novels like Aurora by Kim Stanley Robinson and The Songs of Distant Earth by Arthur C. Clarke delve into the social and psychological challenges of generation ships. They don't always paint an optimistic picture. Robinson's Aurora, in particular, argues that generation ships might be fundamentally flawed, that the technical challenges are insurmountable, that we can't replicate Earth's biosphere in a closed system, and that the human cost is too high. Maybe he's right. Maybe interstellar colonization is a fantasy, a dream that will always remain just out of reach. Or maybe we'll find ways to overcome the challenges, ways we can't even imagine right now. History suggests that humans are pretty good at solving problems when we're motivated enough. We've done impossible things before. Let's consider one more scenario, one that's both optimistic and strange. What if we don't travel to other stars at all? What if we bring the stars to us, in a sense? I'm talking about stellar engineering, manipulating stars themselves to suit our purposes. One concept is the Shkadov thruster, a megastructure that uses a giant mirror to reflect a star's light back on itself, creating a net thrust that slowly moves the star and everything orbiting it through space. Over millions of years, you could steer your entire solar system, turning it into a kind of interstellar spacecraft. You'd take Earth, Mars, all the planets with you, maintaining your home environment while traveling to new parts of the galaxy. The timescales are absurd, millions of years to travel even a few dozen light years, but you wouldn't be confined to a cramped spacecraft. You'd have an entire solar system as your home. You could wait out the journey in comfort, building civilizations, living countless generations, all while slowly drifting toward a new neighborhood in the galaxy. This is the domain of Kardashev Type II civilizations, societies that can harness the entire energy output of their star. We're currently a Type 0.7 or so, able to harness only a fraction of Earth's energy. Getting to Type 2 would require technology so advanced it might as well be magic to us now. But it's not physically impossible. It's just engineering on a scale we've never attempted. Another idea is the Dyson sphere, a megastructure that completely surrounds a star, capturing all of its energy output. You could live on the inside surface of the sphere, or on countless habitats orbiting within it. With that much energy, you could power anything: propulsion systems, life support for trillions of people, even experiments in physics that could unlock new technologies. A civilization that builds a Dyson sphere would have resources beyond anything we can currently imagine. and the question of traveling to other stars might become trivial. But again, these are ideas for civilizations far more advanced than ours. They're worth thinking about because they represent the ultimate potential of intelligent life, the kinds of things that become possible if we survive long enough and keep advancing. They also provide possible answers to the Fermi paradox. If advanced civilizations exist, maybe they've built these kinds of megastructures, and we should be looking for the signatures of such constructions. Stars that dim in unusual ways, infrared radiation from waste heat, geometric patterns that don't occur naturally. These aren't abstract questions, they're urgent and practical. The decisions we make now about funding space programs, about developing technologies, about international cooperation, about how we treat our own planet, those decisions will determine whether humanity becomes a spacefaring civilization or stays confined to Earth until some catastrophe wipes us out. And make no mistake, catastrophe is always a possibility. Earth has been hit by asteroids that caused mass extinctions. Supervolcanoes have erupted and plunged the planet into years of winter. Solar flares could knock out our power grids and communications. And those are just the natural threats. We've also created our own existential risks. Nuclear weapons, engineered pandemics, climate change, artificial intelligence that might not share our values. Any of these could end human civilization or even human existence. That's why space isn't a luxury or a distraction from problems here on Earth. It's insurance. It's our backup plan. If we have self-sustaining colonies on Mars and orbital habitats and mining operations in the asteroid belt, then no single event can wipe us all out. We become resilient. We buy ourselves time to solve our problems, to mature as a species, to reach our potential. But getting there requires vision and commitment. It requires investing in research and development, in education, in the infrastructure of space exploration. It requires looking beyond the next election cycle or quarterly earnings report and thinking in terms of decades and centuries. It requires cooperation between nations, between public and private sectors, between current and future generations. Think about the Apollo program. At its peak in the mid-60s, NASA's budget was over 4% of the entire federal budget of the United States. That's the equivalent of about $100 billion per year in today's money. It was a colossal effort, mobilizing hundreds of thousands of people, pushing the boundaries of technology and engineering. And it worked. We put 12 people on the moon between 1969 and 1972. Then we stopped. The political will evaporated, the budget was slashed, and we haven't sent anyone beyond low Earth orbit since Apollo 17 in December 1972. That's over 50 years ago. For half a century, humans have been circling Earth, going nowhere farther than a few hundred kilometers up, while our robots explore the solar system in our place. Now, there's nothing wrong with robotic exploration. Robots are cheaper, don't need life support, can go places too dangerous for humans, and can operate for years or decades. The Voyager probes are still sending back data after nearly 50 years in space, having traveled farther than any human-made object. The Mars rovers have explored the Martian surface in detail, finding evidence of ancient water and habitable conditions. The Cassini mission revealed the wonders of Saturn and its moons. Robots are essential tools, but they're not us. They don't experience wonder or curiosity. They don't make intuitive leaps or creative decisions in the moment. They don't inspire people the way a human stepping onto an alien world inspires people. There's something profound about human presence, about knowing that someone like you, flesh and blood, is standing in a place no one has stood before. When Neil Armstrong stepped onto the moon, 600 million people watched on television, about 20% of the entire human population at the time. It was a shared moment of triumph, proof that humans could do the impossible. It inspired a generation of scientists and engineers. It showed us that our potential is limited only by our imagination and will. We need more of those moments. We need to see humans walking on Mars, diving into the ice of Europa, standing on the rings of Saturn, not just because it's exciting, though it is, but because it reminds us what we're capable of. It gives us hope and direction. It unites us in a common goal that transcends borders and politics. So let's talk about Mars in more detail, because that's the next big goal, the next place humans will set foot beyond the moon. Mars is in many ways the best destination in the solar system for human exploration and eventual colonization. It's relatively close, with travel times of 6 to 9 months using current propulsion technology. It has a day length of about 24.5 hours, very close to Earth's, which makes it easier for humans to adapt. It has seasons, ice caps, mountains, valleys, and canyons that dwarf anything on Earth. Mars also has resources. There's water ice in the polar caps and likely in underground deposits. The atmosphere, thin as it is mostly carbon dioxide, which can be used to produce oxygen and methane fuel through chemical processes. The soil contains minerals that could be used for construction. With the right technology, you could build habitats, grow food in greenhouses, and produce fuel and oxygen locally, reducing the need to bring everything from Earth. The challenges, of course, are immense. The atmosphere is less than 1% the density of Earth's, so you can't breathe it and you need a pressure suit to survive. The temperature averages -60 degrees Celsius, though it can range from -125 at the poles in winter to +20 at the equator in summer. Radiation levels are high because Mars lacks a strong magnetic field and thick atmosphere to shield the surface. Dust storms can envelop the entire planet for months, reducing solar power availability. But none of these challenges are insurmountable. We have the technology to build pressurized habitats and spacesuits. We can generate power with nuclear reactors or solar panels supplemented with batteries. We can shield habitats with sandbags or bury them underground. We can grow food in hydroponic systems using LED lights. NASA and private companies like SpaceX are actively working on the technologies and missions that will take humans to Mars. Elon Musk has been particularly vocal about his goal to establish a self-sustaining city on Mars, with a population of 1 million people within 50 to 100 years. That's an audacious goal, maybe even unrealistic, but it's driving development of the Starship rocket, a fully reusable launch system designed to carry up to 100 people and 100 tons of cargo to Mars. If even a fraction of that vision is realized, it would represent a monumental leap in human spaceflight capability. The first Mars missions will likely be science-focused, with small crews spending a year or two on the surface conducting research before returning to Earth. But if those missions are successful, if we prove we can live and work on Mars, then the next phase will be establishing a permanent presence, a base that's continuously inhabited like the International Space Station but on another planet, and from there expansion, more bases, more people, more infrastructure. Eventually, if things go well, Mars could become a second home for humanity, not a replacement for Earth, but a complement, a place where millions or even billions of people live and work and build their own societies. Terraforming Mars, transforming it into an Earth-like planet with a breathable atmosphere and liquid water on the surface, is often discussed as the ultimate goal. That would take centuries or millennia and require technologies we don't yet have, like releasing greenhouse gases to warm the planet or importing volatiles from comets and asteroids. But it's not physically impossible. Imagine hundreds of years from now, looking at Mars through a telescope and seeing blue and green instead of red, seeing oceans and forests and cities glittering at night, knowing that humans, your descendants, did that. That we took a dead, frozen desert and brought it to life. That's the dream anyway. The reality might be messier and slower and more complicated. It always is. But the dream matters because it gives us something to aim for, a vision of a future where humanity isn't confined to one fragile planet, where we've diversified and spread out across the solar system and maybe beyond. Let's zoom out for a moment and think about the timeline. Where are we now, and where might we be in 50 years, 100 years, 500 years? Because understanding the possible trajectories helps answer the original question about how far one human can travel in a lifetime. Right now, in 2026, we're on the cusp of a new era in space exploration. NASA's Artemis program is working to return humans to the moon, with plans for a sustained presence and a lunar gateway station that will serve as a staging point for deeper space missions. China has also announced ambitious plans for lunar bases. SpaceX is developing Starship. Other private companies are working on space tourism, satellite constellations, and asteroid mining concepts. In the next 10 to 20 years, we'll likely see the first humans on Mars. The infrastructure around Earth will expand dramatically, with more space stations, satellite servicing, and perhaps the first commercial space hotels. The Moon might have a small research base similar to Antarctic research stations, with rotating crews. By mid-century, let's say 2075, if things go well, there could be a permanent settlement on Mars with hundreds of people. The Moon might have a larger base, possibly even some industrial activities like mining helium-3 for fusion reactors or manufacturing materials in lunar gravity. Asteroid mining might be getting started with robotic systems and perhaps a few human-tended facilities. Orbital infrastructure around Earth will be extensive, with thousands of people living and working in space. Earth to Mars travel will still take 6 to 9 months, but it will be routine, with multiple ships launching during each transfer window every 26 months when Earth and Mars are favorably aligned. The experience might be comparable to an extended sea voyage in the age of exploration, uncomfortable and risky, but manageable with proper preparation. By the end of the century 2100, we might see the beginnings of true space-based civilization, multiple settlements on Mars, growing in size and independence, mining operations throughout the asteroid belt, research stations on the moons of Jupiter and Saturn, studying those fascinating worlds and searching for signs of life in subsurface oceans. Perhaps the first O'Neill cylinders, massive rotating habitats in space that don't depend on any planetary surface. At this point, someone born on Mars might spend their entire life moving between Mars, the asteroid belt, and various orbital habitats, covering distances of billions of kilometers without ever setting foot on Earth. Their home would be the inner solar system, a three-dimensional territory incomprehensibly larger than Earth's surface, and all of it accessible within their lifetime using advanced but realistic propulsion systems. Now push forward another century to 2200. If the expansion continues, if we develop fusion propulsion or other advanced drives, the entire solar system becomes humanity's playground. There could be settlements or at least regular human presence everywhere from Mercury to the Kuiper belt. Travel times shrink. A trip from Earth to Neptune that would take decades with current technology might take just a few years with a high-powered fusion drive that can maintain constant acceleration. Someone living in this era could, over the course of a normal human lifetime, visit every planet and major moon in the solar system, covering trillions of kilometers. They might be born on Mars, study on Titan, work on an asteroid mining operation, retire to an O'Neill cylinder orbiting Jupiter. Their experience of travel would be utterly alien to us, just as a modern intercontinental jet traveler's experience would be alien to someone from the 15th century who never traveled more than 100 kilometers from their birthplace. And this is all without invoking any speculative physics or radical life extension. This is just engineering, extrapolating from technologies we already have or can reasonably foresee. Chemical rockets got us to the moon. Ion drives and nuclear propulsion can get us to the outer solar system efficiently. Fusion propulsion, which is still theoretical but based on solid physics, could make the entire solar system accessible within human lifetimes. But let's say we do get radical life extension. Let's say medical technology advances to the point where aging is treated like any other disease, where regenerative medicine and genetic therapies can keep a human body functional for centuries instead of decades. This isn't pure science fiction. There's active research in this area, studying organisms that live extremely long lives or don't seem to age at all, trying to understand the mechanisms and apply them to humans. If your lifetime is measured in centuries instead of decades, then even with slower propulsion systems, the stars come within reach. A 50-year journey to Alpha Centauri, which would consume most of a normal human lifespan, becomes just a significant but not overwhelming fraction of a 500-year life. You could make the journey, spend centuries exploring the new system, and potentially even return to tell the tale, though by the time you got back, everyone you knew would be long gone and the world would have changed beyond recognition. This introduces a strange kind of time dilation, not the relativistic kind from traveling near light speed, but a social and psychological one. If you leave for a 50-year journey and return after another 50 years away, you've been gone a century. Earth has changed, technology has advanced, languages have evolved, the political landscape is completely different. You're a time traveler of sorts, not through relativistic effects, but just through the vast distances and durations involved. People talk about this in the context of generation ships, the idea that the people who arrive at the destination won't be the ones who left, that it's their great-great-grandchildren who will see the new world. But that assumes normal human lifespans. If we extend lifespan significantly, then the psychological and social dynamics change. The person who makes the decision to go is the same person who arrives. They bear the full consequences of their choice. That might make people more cautious, more thoughtful about committing to such a journey. Or it might make them more willing, knowing they'll see the outcome themselves. There's also the possibility of suspended animation or cryogenic preservation. If you could be frozen or put into some form of hibernation for the duration of the journey, then subjectively the trip would be instantaneous. You'd go to sleep in the solar system and wake up at Alpha Centauri. For you personally, no time would have passed, but objectively, decades would have elapsed. Your friends and family back home would have aged or died. The world would have moved on without you. This is a common trope in science fiction, from 2001, A Space Odyssey, to Alien to Avatar. The travelers sleep while the ship carries them across the void. It's an elegant solution to the problem of long journey times, but it's still mostly theoretical. We don't have a proven method for safely putting humans into stasis for years or decades. There's been some progress with cooling and preserving organs for transplant, and some animals can survive freezing, but a human is vastly more complex. The main challenge is ice crystal formation. When water freezes, it expands and forms crystals that puncture cell membranes, essentially shredding tissue at the microscopic level. You can use cryoprotectants, chemicals that prevent ice formation, but they're often toxic at the concentrations needed. Some researchers are working on vitrification, turning biological tissue into a glass-like state without ice crystals, but scaling that up to an entire human body and then successfully reversing the process is still far beyond our current capabilities. But let's say we figure it out. Let's say in 50 or 100 years, we have safe, reliable suspended animation. Suddenly, the galaxy opens up in a new way. You could travel for hundreds or thousands of years. Age-wise, you'd be only a few years older. You could visit dozens of star systems in what would feel like a single lifetime to you, though thousands of years would pass in the outside universe. This creates a bizarre scenario where interstellar explorers become disconnected from the timeline of Earthbound humanity. You leave in 2200, travel to a star 30 light-years away, taking 60 years ship time but only a few subjective years in suspension. You explore for a decade, then travel to another star 40 light-years away, taking another 80 years. By the time you return to Earth, if you ever do, it's the year 2400 or beyond. Everything you knew is history. You're a relic, a living fossil from another age. This is the strange mathematics of interstellar travel. Even without relativity, even at sublight speeds, the distances are so vast and the journeys so long that time becomes distorted. You can't have a normal relationship with home. You can't maintain friendships or family ties across decades or centuries of separation. You become a nomad, a wanderer, your connections to other travelers or to the new worlds you discover, not to the civilization you left behind. Some people might embrace that. The ultimate freedom, the ultimate adventure, unmoored from the past and open to whatever the future brings. But others would find it unbearable, the loss of everyone and everything they knew, the loneliness of being unstuck in time. And we haven't even talked about relativistic effects yet. If you could somehow accelerate a spacecraft to a significant fraction of the speed of light, say 10%, 20% or higher, then Einstein's special relativity comes into play. Time dilation means that time passes more slowly for you, the traveler, than for people back on Earth. The faster you go, the more pronounced the effect. At 90% of light speed, time for you moves at less than half the rate of time for someone at rest. A journey that takes 50 years by Earth's clocks would feel like only about 22 years to you. At 99% of light speed, the dilation factor is about 7. That same 50-year journey would feel like just 7 years. At 99.9%, it's about 22 times dilation. 50 years becomes only 2.5 years for you. This is real physics, proven experimentally with atomic clocks and particle accelerators. It's not speculation. If we could build a ship that travels at these speeds, time dilation would absolutely happen. The practical problem, of course, is getting a ship to those speeds. The energy requirements are staggering. The kinetic energy of an object is 1/2 its mass times its velocity squared. As you approach the speed of light, relativistic effects kick in and the energy required increases toward infinity. You can never quite reach light speed if you have mass, but you can get arbitrarily close with enough energy to accelerate even a small spacecraft, say 1,000 kilograms, to 90% of light speed would require energy equivalent to about 400 million tons of TNT, comparable to the largest nuclear weapons ever built, and that's the kinetic energy alone, not accounting for inefficiencies in the propulsion system. And then you need to slow down at the other end, which requires the same amount of energy again. The only realistic way to do this with known physics is through matter-antimatter annihilation, which converts mass directly into energy with 100% efficiency. But we can't produce antimatter in any significant quantity, and storing it safely is an enormous challenge since it annihilates instantly on contact with normal matter. Another approach is the laser light sail concept, which I mentioned earlier. You don't carry your fuel with you. Instead, a massive array of lasers back in the solar system pushes against a lightweight reflective sail attached to your spacecraft. The lasers stay on for years, continuously accelerating the sail until it reaches a significant fraction of light speed. The spacecraft itself can be very light, just the payload and sail, because there's no propulsion system or fuel. Breakthrough Starshot, a research program funded by the Breakthrough Initiatives, is exploring this concept with the goal of sending tiny gram-scale probes to Alpha Centauri at 20% of light speed. They'd get there in about 20 years, plus another 4 years for the signal to come back, so 24 years total from launch to receiving data. That's within a human lifetime, barely, though the probes themselves aren't carrying humans, just miniaturized instruments and cameras. But could you scale this up to carry a human? In principle, yes, but the engineering challenges multiply enormously. A habitat large enough for even one person, with life support, radiation shielding, and provisions for a decades-long journey, would mass many tons. The sail would need to be correspondingly huge, kilometers across perhaps, and the laser array would need to be proportionally more powerful, requiring energy outputs comparable to a significant fraction of all the power humanity currently generates. It's not impossible, but it's a mega project on a scale we've never attempted. It would require global cooperation and resources, a sustained commitment over decades just to build the infrastructure before the first ship even launches. And there's no way to slow down at the destination unless you build another laser array there, which you can't do until you've already sent something there to build it, which brings you back to the slow boat problem. So maybe the first human starship wouldn't try to slow down. Maybe it would be a flyby mission, screaming through the target system at a significant fraction of light speed, gathering data for a few hours or days as it passes, then continuing on into the void forever. The traveler would know they're never coming back, never stopping, just observing and transmitting data back to Earth as they fly through system after system. A one-way journey into the infinite black. That's a lonely fate, almost incomprehensibly so. But maybe, for some people, it would be worth it. To see things no one else has ever seen, to be the first human presence in another star system, to contribute knowledge that would outlive you by millennia. There's a certain nobility in that sacrifice, a grandeur in giving yourself to the cause of exploration, even knowing the cost. Or maybe we're thinking about this wrong. Maybe the future of interstellar travel isn't physical ships at all, but information. If we can map a human consciousness completely, every neuron and synapse, every memory and thought pattern, then in principle that information could be transmitted as a signal at the speed of light. You'd be converted into data, beamed across space to a receiver at the destination, and reconstructed there in a new body, biological or synthetic. This is essentially teleportation, not of matter but of mind. The original you might still exist back on Earth, or maybe the scanning process is destructive and the transmitted copy is the only you that remains. That gets into deep philosophical questions about identity and continuity of consciousness. Is the reconstructed person really you, or just a copy that thinks it's you? If both versions exist, which one is the real you? These aren't just academic questions. They have profound implications for how we think about interstellar travel and what it means to be human. If we embrace mind uploading and transmission, then the galaxy becomes accessible at light speed. You could visit a star 100 light-years away in subjectively zero time from your perspective, though 100 years would pass for everyone else. You could make copies of yourself, send them to 1,000 different stars, each one exploring and reporting back. You'd become distributed, a network of selves spread across the galaxy. Some people find this idea exciting, liberating even. You're no longer trapped in a fragile biological body, bound by the laws of physics and mortality. You're pure information, endlessly copyable and transmittable, potentially immortal as long as your data is preserved. Others find it horrifying. You've lost your body, your physical connection to the world. You're not really human anymore, just a simulation, a ghost in the machine. And if copies can be made, then what does individuality even mean? Are you really still you, or have you become something else entirely? I don't have answers to these questions. I'm not sure anyone does. They're at the frontier of philosophy and technology, and we'll have to grapple with them if and when these capabilities become real. What I can say is that they represent possible paths forward, different ways of approaching the fundamental constraints of space and time. So let's try to synthesize all of this into a comprehensive answer to the original question. How far can one human travel in one lifetime? With current technology, in a normal human lifespan of 70 to 80 years, you could travel throughout the inner solar system, visiting the Moon, Mars, the asteroid belt, covering distances of hundreds of millions to a few billion kilometers. That's already extraordinary by historical standards, but it's a tiny fraction of the solar system and an infinitesimal speck compared to interstellar distances. With near-future technology in the next 50 to 100 years, advanced propulsion like fusion drives or nuclear electric, possibly combined with moderate life extension, you could explore the entire solar system out to Neptune and beyond, covering trillions of kilometers. You might visit a dozen different worlds, spend years on each, and still return to your starting point within your lifetime. With more speculative but still physics-based technology, things like antimatter propulsion or laser light sails, combined with significant life extension or suspended animation, you could potentially reach the nearest stars within your lifetime. Alpha Centauri, Barnard's star Sirius, stars within 10 to 20 light-years become accessible, though the journey would consume decades and you'd return, if you returned at all, to a world that had moved on without you. With relativistic travel, approaching the speed of light through some currently unknown propulsion method, time dilation opens up the galaxy. From your subjective perspective, you could travel hundreds or even thousands of light years within what feels like a single lifetime, though thousands of years would pass back on Earth. You'd be a time traveler, jumping forward through the centuries, exploring a galaxy that's ancient and ever-changing, and with truly radical technologies, mind uploading, consciousness transfer, technologies that divorce your identity from your biological body, distance becomes almost irrelevant. You could traverse the entire galaxy at light speed as pure information, experiencing the journey as instantaneous, awakening in new bodies or substrates at destinations tens of thousands of light years away, though tens of thousands of years would pass in objective time. Each of these scenarios represents a different relationship with space, time, and identity. Each comes with its own constraints, possibilities, and philosophical implications, and importantly, none of them violate the laws of physics as we understand them. They're all at least theoretically possible, even if some are far beyond our current engineering capabilities. The answer, then, is that it depends. It depends on when you live, what technologies are available, what risks you're willing to take, and what you're willing to sacrifice. A human born today, with today's technology, might travel a few 100 million kilometers in their lifetime if they're lucky enough to be selected for a Mars mission. A human born 100 years from now might travel trillions of kilometers, visiting dozens of worlds across the solar system. A human born 500 years from now might reach the stars, covering distances measured in light years. Though the meaning of lifetime might have changed by then, there's another dimension to consider too, and that's the question of why. Why travel these distances? What's the purpose? Throughout history, humans have explored for various reasons: survival, resources, curiosity, glory, escape. The motivations for space exploration are similarly varied. Some people are driven by pure curiosity, the desire to see what's over the next horizon, to answer fundamental questions about the universe and our place in it. Are we alone? Is there life on other worlds? What's out there in the vast darkness between stars? These are questions that have haunted humanity for as long as we've looked up at the night sky. Others are motivated by survival and pragmatism. Earth is finite, Resources are limited. Populations grow. The sun will eventually die. If humanity is to survive long-term, we need to spread beyond Earth, to diversify our habitats, to ensure that no single catastrophe can wipe us out. Space exploration is insurance, a hedge against existential risk. Still others see economic opportunity. The asteroid belt contains more metal and minerals than humanity has extracted from Earth in all of history. The energy available from the sun dwarfs all fossil fuels combined. Space-based solar power, asteroid mining from the lunar surface for fusion reactors could be the foundation of a post-scarcity economy where energy and raw materials are essentially unlimited, and some are driven by idealism or even escapism. The chance to build new societies, to try different ways of organizing human communities free from Earth's baggage of history and politics. The chance to start fresh, to pioneer, to be part of something larger than yourself. Or conversely, the chance to get away from the problems and conflicts of Earth, to find peace and solitude in the vast emptiness of space. All of these motivations are valid, and they'll all play a role in driving humanity's expansion into space. The key is that it's not just one thing. Space exploration serves multiple purposes, appeals to different values, offers different rewards. That diversity of motivation is part of what will sustain the effort over the long term, through setbacks and challenges, through the inevitable accidents and tragedies, because there will be tragedies. Space is unforgiving. We've already lost astronauts and cosmonauts in accidents, from the Apollo 1 fire to the Challenger and Columbia disasters to the Soyuz 1 and 11 tragedies. As we venture farther and attempt more ambitious missions, there will be more losses. Ships will fail, life support systems will malfunction, people will die far from home, their bodies never recovered, their last moments unwitnessed except by their crewmates. This is the cost of exploration, and it's a cost we have to be willing to bear if we're serious about expanding into space. Not recklessly or carelessly, we should do everything possible to minimize risk and maximize safety, but with the understanding that we can't eliminate risk entirely. The frontier has always been dangerous. The early sailors who explored Earth's oceans knew they might not return. The same will be true for space explorers. But I believe it's worth it, not just for the practical benefits or the scientific knowledge or the economic opportunities, though all of those are valuable, but for something deeper and harder to quantify. The expansion into space represents the continuation of the human story, the next chapter in a narrative that began when our ancestors first walked upright on the African savanna. We are explorers by nature. It's in our DNA, literally. The genes that drove some humans to leave Africa and spread across the globe are still with us. The curiosity, the restlessness, the desire to see what's beyond the horizon, these are fundamental parts of being human. Staying confined to Earth, never venturing beyond this one world, would be a betrayal of that heritage. More than that, space offers us perspective. The overview effect, the cognitive shift reported by astronauts who see Earth from space, the realization of how small and fragile our planet is, how arbitrary our borders, how interconnected we all are. That perspective is desperately needed in a world still divided by nationalism, tribalism, and short-term thinking. If more people could see Earth as astronauts see it, a beautiful blue marble floating in the infinite black, no visible boundaries, just one world, one humanity sharing one common home, maybe we'd make better decisions about how we treat that home and each other. And as we establish ourselves on other worlds, as we become a multi-planet species, maybe we'll develop an even broader perspective, a solar system-wide or galaxy-wide consciousness that transcends the petty divisions that have plagued us throughout history. That's aspirational, maybe naive, but I think it's a goal worth pursuing. And the journey itself, the process of expanding into space, will change us in ways we can't predict. New environments will drive new adaptations, biological and cultural. People born on Mars, growing up in 1/3 Earth's gravity, will be physically different from Earth-born humans, taller and lankier, their bones and muscles adapted to the lower gravity. They might never be able to visit Earth, unable to withstand the crushing weight of full gravity. Isolated communities on distant worlds will develop their own cultures, their own languages and customs, diverging from Earth's mainstream. After generations, they might not even consider themselves the same species anymore. Speciation, the process by which one species splits into two or more, could happen to humanity if populations become sufficiently isolated for long enough. This isn't necessarily a bad thing. Diversity is strength, biologically and culturally. A galaxy full of different human variants, each adapted to their environment, each contributing their unique perspectives and innovations, might be more resilient and creative than a homogeneous humanity. But it does raise questions about identity and unity. What does it mean to be human if there are multiple types of humans, some biological, some cybernetic, some uploaded minds, some genetically engineered for specific environments? What holds us together as a species, as a civilization, if we're spread across distances so vast that communication takes years or decades? These are questions our descendants will have to answer. We can't predict how it will all turn out, what challenges they'll face, what solutions they'll devise. All we can do is take the first steps, build the foundations, and trust that future generations will continue the work. So where does that leave us? Here in 2026, thinking about how far one human can travel in a lifetime, it leaves us at a crossroads, at the beginning of something momentous. The choices we make now, individually and collectively, will shape the possibilities for those who come after. If we invest in space technology, if we support exploration and research, if we educate the next generation of scientists and engineers and instill in them a sense of wonder about the cosmos, then the humans of the future will travel farther than we can imagine. If we turn inward, if we prioritize short-term concerns over long-term vision, if we let fear and division prevent us from reaching beyond Earth, then the answer to our question might remain tragically limited. The distance one human can travel in a lifetime is not a fixed number. It's a variable dependent on choices we haven't made yet, technologies we haven't invented yet, societies we haven't built yet. It's a question whose answer changes with time, expanding outward as our capabilities grow. If you are still watching, make sure to give this video a like and subscribe to the channel. You'll be joining a community of curious minds exploring the cosmos together, and you'll never miss out on the big questions that make us human. Right now, a human astronaut on the International Space Station travels about 7.66 kilometers per second in orbit, circling Earth every 90 minutes. In a single day, they cover over 600,000 kilometers. Over a 6-month mission, that's more than 100 million kilometers, though they're going in circles and never actually leave Earth's vicinity. It's distance without true travel, motion without journey, but the potential is there. The technologies exist or are being developed. The vision is taking shape. We're closer now than we've ever been to becoming a spacefaring civilization, to making the solar system and eventually the galaxy accessible to human explorers. In your lifetime, you might see humans return to the moon and establish a permanent presence there. You might see the first footsteps on Mars, the first children born on another world. You might see asteroid mining become a reality, space tourism become affordable, orbital habitats become home to thousands of people. If you're young enough, and if medical technology advances as some predict, you might live to see fusion drives and laser sails, to see humans venture to Jupiter's moons or Saturn's rings. You might see the first ships launch toward other stars. knowing that their occupants or their descendants will arrive at destinations you can barely imagine. And if you're really fortunate, if everything breaks right and the pace of advancement continues to accelerate, you might yourself have the opportunity to leave Earth, to see the planet from orbit with your own eyes, to experience weightlessness, to witness the silent beauty of space firsthand. That's no longer a fantasy reserved for a handful of government astronauts. Private space companies are making it possible, slowly, gradually, for more people to access space. The cost is still prohibitively high for most, but it's dropping. The first orbital flights cost billions and were reserved for nation-states, then hundreds of millions. Now commercial flights are in the tens of millions. Suborbital tourism is in the hundreds of thousands. The trajectory is clear. In 20 years, maybe 30, orbital access might be comparable to buying a luxury car. In 50 years, it might be comparable to an expensive vacation. In a century, it might be routine. That's the power of technology and economies of scale. What starts as impossibly expensive and rare becomes common and accessible. Air travel followed this pattern. Computers followed this pattern. Space travel will follow this pattern. So the answer to how far one human can travel in one lifetime keeps expanding. For your grandparents' generation, it might have been a few thousand kilometers traveling by ship or train across continents. For your parents' generation, it's tens of thousands of kilometers flying around the world multiple times. For your generation, it might be hundreds of millions of kilometers, traveling through cislunar space and perhaps to Mars. For your children's generation, it could be billions of kilometers, routine travel throughout the solar system. For your grandchildren, trillions of kilometers, voyages to the outer planets and beyond. For generations farther removed, light years, journeys to other stars, though by then the meaning of distance and lifetime might have changed so fundamentally that the comparison becomes meaningless. This is the trajectory we're on if we stay the course, not a guarantee. Things could go wrong, progress could stall, civilization could collapse, but a real possibility, a plausible future based on the trends and technologies we can see today. The universe is vast beyond comprehension. The distances between stars are so enormous that light itself, the fastest thing that exists, takes years to cross them. In that context, a single human lifetime is a fleeting moment, barely a blink. And yet, within that moment, with the right tools and determination, a human could potentially traverse distances that would have seemed like pure fantasy to anyone living before the space age. We've come so far in just a few generations. From the Wright brothers' first flight in 1903 to the moon landing in 1969 was only 66 years. From Sputnik, the first artificial satellite, to the International Space Station was only 42 years. The pace of advancement is breathtaking when you step back and look at it. Who knows what the next 60 years will bring, or the next 100? The only certainty is that humans will keep pushing, keep exploring, keep reaching for what seems impossible. It's what we do, it's who we are. So how far can one human travel in one lifetime? As far as we dare to dream and work to achieve. The limit isn't in the stars, it's in ourselves, in our courage and vision and willingness to attempt great things knowing we might fail. The universe is waiting. The question is whether we'll answer the call, whether we'll step out into that vast darkness and make it our own, or whether we'll stay here on Earth, looking up and wondering what might have been. I believe we'll go, not because it's easy, as President Kennedy said, but because it's hard, because that challenge is one we're willing to accept, one we're unwilling to postpone, and one we intend to win. The journey of 1,000 light years begins with a single step. We've already taken that step. The footprints on the moon are still there, preserved in airless silence, waiting for us to return and continue the journey. How far can one human travel in one lifetime? Here's the thing though, Every limit I just mentioned disappears if we can travel faster than light. I made an entire video exploring what it would actually take. It's on screen now. Make sure to check it out. You won't regret it.